So I'm very honored and very happy to be able to participate in the celebration of Dan's birthday and his receipt of the Wolf Prize. I remember when I came here to Yale, it was 1970. I was still in my 20s, and after I came here, Dan was chairman. And he took care of me in every way. It's in the settling in and all aspects of department life and social life. And also, more important, he changed the direction of my research. Because before I came, I was working on something else, and then afterwards I went into this whole area of rigidity. It's I was, of course, in this building, my office. I remember Dan's office on the 4th floor, more or less at the end. And at one time, first I had office here on the 2nd floor, and then moved up. I was told that now the chair is my office. And then Dan told me about his work, about refraction subgroups to try to produce non-arithmetic lattice. And he was using a lot of computers in those days. And at one point, he did not quite yet get the discrete subgroup, the almost discrete subgroup, and he wondered what could be done with it. And that's the point that I was introduced to his great work. So we were trying to compute various things, volumes, Chern cars, and so forth. One thing that really shocked me was that Dan was 20 years my senior. I think he's still 20 years my senior. But when we're trying to compute things in hyperbolic geometry, all these hyperbolic signs and so forth, when you actually really want to compute things, you have to do things arithmetically. And he could do it at tremendous speed. And I was 20 years his junior, so I was sort of very slowly writing down. He could just do like this. I was extremely shocked. I mean, this guy's his intellectual power is just fantastic. So I sort of one day timidly asked him, how could you compute so fast? He was very modest. He told me that he spent 4 years doing this during the war. He was teaching people how to fire cannons. And the cannons had such a big range that the curvature of the Earth had to be taken into account. So he was using spherical functions, not the hyperbolic ones. But of course, the change of sign, even with the change of sign, you could do it without mistake quickly. It's still a tremendous feat. And so this thing I distinctly remember. I don't know whether Dan remember this or not. So after that, I studied his work, and I saw this wonderful treasure. So I went into it and tried to understand it. And of course, his contribution not only changed my direction, but changed the direction of many, many people, I think. And since my background is more in complex geometry, so I have been quite biased, so looking at the complex side of it, especially the Kaehler and complex geometric side of it. There's another thing that sort of accidentally pushed me into this area. It was a casual conversation with Kakutani, another colleague here. And one time we were chatting. Kakutani was talking about his youth, and then I asked him about the pre-war days. I mean, he was writing papers in German, so he told me about his work. And then one thing he tried to explain to me was the relation between harmonic maps and random walk, algorithmicity, and so forth, harmonic functions and harmonic measures. So actually, it had nothing to do with Dan's work, but it sort of stayed in my mind. So I was looking at Dan's work because he was looking, as Kurt so magnificently reproduced with color pictures of his algorithmicity at the boundary. So at that point, I went into it because I try to use geometric methods to understand Dan's. So to me, Dan's work is a question of getting something much more than the given topological condition. So you're given topological condition and you want to conclude from it much more, say like metric conditions, like group conditions. So the starting point in the work going into algebraic geometry from Dan's important foundation is the question of perfect square. So it actually started out already from elliptic operators. So when you try to solve an equation, let's say Laplacian E equal to F. So it's a single equation, but then you could get much more from it. Let's say you get the estimate of first order derivative and so forth, even though it's a single equation, but you could get estimates of the others, something like this, just by integration by parts. So, so this situation is a matter of writing this operator as sum of the squares. Okay, so this thing here, of course, would be, of course, it's given already as sum of squares. Okay, so if you look at it from the point of view of symbols, so it would be a quadratic polynomial. And it's a quadratic polynomial written as sum of squares plus something. So it's the usual way of solving quadratic equations. Okay. So I mean, I never could get this formula right, but it's something like this, I think. Plus 4ac minus b squared 4a something. Okay. So what happens is that for this kind of situation, of course, it's already given. But in general, when you have a second order differential operator and you write down in symbols, you could always apply the completion of squares to it. And of course, the completion of squares would give you information only after you integrate by parts. So when you regard the operator as an operator on the Hilbert space, so to speak, when you take it's a positive definite and so forth in that sense. Okay. So when you look at Dan's work of using properties of hyperbolic space, actually in geometry it is the question of curvature. So you start out with curvature, and then from curvature you want to say that given any topological condition, of course up to homotopy, then you could actually find a great deal of information, a great deal of properties. And the main thing is the completion of squares, a perfect square. So the first thing that could be done from that point of view is a map. Let's say you start out with a map from M. Let's say it's a compact Kaehler manifold into another manifold. Yeah. And if you look at Dan's situation, it would be in the case of, let's say, a compact quotient of an irreducible bounded symmetric domain. Because you have to rule out the case of complex dimension 1, so if of complex dimension at least 2. So that was the starting point. And there, one wants to get this elliptic operator in to complete the square. So if you are given a homotopy class, So inside this homotopy class, you try to minimize something. And what is being minimized is the energy. Okay. So when you minimize the energy, actually this is a generalization of the situation of geodesics. So when you look at geodesics, closed geodesics, then you are looking at the S1 inside N, for example. Okay. And then, of course, geodesic, you could minimize the length, or you can minimize the energy. Actually, it doesn't really matter that much. So if you have F here, you could minimize F, let's say, to alpha. Alpha is bigger than 1/2. They will give you the same result if you look at the arc length when you do the computation. So in this case, when you try to minimize it, you take the steepest descent. So you take the Euler-Lagrange equation, okay, and get the gradient, and you deform to descent. And then you get the answer. Of course, in order to get the answer, you have to get some condition. If you get the descent would be like df dt, sort of like minus Laplacian, Laplacian of df, I think. Yeah. This is from the Euler-Lagrange equation of integrate by parts to go over. Okay. So there, you would get the heat equation to do it. And then in order to make sure that the limit is achieved, you need some Ascoli-Azella argument. Ascoli-Azella argument. And the Ascoli-Azella argument needs some estimates. And the estimate that is needed actually would be something like this. If you take the energy, which is this one here, okay, then you would, when you write it down, if the curvature, the sectional curvature of n is non-positive, you would get less than or equal to just a constant times the energy. Okay. And then there, you could use the maximum principle for the heat operator, okay, and to make sure that this thing is bounded in soup norm if you proceed. And then the Kaehler theorem works. Okay. So in the case of the curve, you have the usual Jacobi field or second variation of the arc length. And the generalization to the high-dimensional case is the same. It was done by Eels and Sampson. Of course, it has nothing to do with complex structure. As long as it's semi-positive, this thing holds. Okay. So once you get it, you would get a harmonic map. So the harmonic map actually is the generalization of the geodesic in the high-dimensional case. And so you take the harmonic map equal to 0. Okay. When you take harmonic, you have to interpret in terms of the connections here and here. So you start out with something topological, and then you want to derive some more properties from it. So you appeal to this idea of the elliptic operator and the computational square to try to handle it as sort of classical, and then you get to the harmonic one. And then from a harmonic one, you want to show that you get something more than that by integration by parts, essentially. So you want to say that either this one is equal to 0 or d bar f equal to 0. Okay. So how is this done? This actually is the same as Kodaira's vanishing theorem, the same as Bogner's technique. So for Kodaira's vanishing theorem, there are two forms of it. One is x, the line bundle, plus kx equal to 0 for all p bigger than or equal to 1 when this one is positive, or you have this one equal to 0 for all p less than a dimension of x for if L is negative. Of course, one is actually a dual of the other. Okay. And the way the dual works is that you actually have, in this case, in either case, let's say the case p equal to 1. Okay. And it is because of this condition that this is needed. That actually is the reason why this is needed. So what happens is that you pull back, so you have a harmonic map, let's say x and y, for example. Okay. You can pull back the tangent bundle by f, and then take the d bar of that. So d bar pulls it back. So this is d bar valued 0, 1 form on x, which is d bar of f. You pull it back. And then you want to apply this one here, completion squares. And if the curvature condition is correct, that means this is less than 0, then it forces this one to be 0. So it will be holomorphic already. So the only question is to interpret the notion of curvature. So the curvature here is a bit more complicated because the curvature comes from this guy here. Okay. And this guy has to be pulled back first. And the pullback depends on f. So when you compute it, you actually get a condition involving R of sort of df, d bar f, df, d bar f. Okay. So the curvature looks like this thing wedge, and then it's symmetric here. That's what the curvature is. Yeah. So there's a wedge being involved. Okay. So when you pull back, of course, the df is involved. But since you have taken the d bar already here, so the extra one will be here. So when you take something like this, and you say that this is less than or equal to 0, then this is now known as the complexified curvature, or complexified sectional curvature less than or equal to 0. Because when you look at the curvature, R usually is real. XY, let's say XY, XY or something, or YX, doesn't matter. Okay. So when you allow complex values, so X, for example, is equal to SIT, and then Y equal to UIV, then it becomes the curvature operator condition. And this curvature operator condition, it turns out to be the natural one for the vanishing. So the important thing for this kind of situation is that if you take compare quotient, you do so with compare symmetric manifold. And if the rank of this is sufficiently large, for example, that's always the case if, for example, if this is a homotopy equivalence, then it's sufficiently large. Okay. So when it's sufficiently, the reason why I need sufficiently large is that you have this term to help you either force this thing to be 0 or this thing to be 0. But in the case of bounded symmetric domains, you may have some flat direction. So you have to have enough directions that is negative enough to force this to happen. Okay. So this was actually the first step of using Dan's idea of getting this strong rigidity. Okay. So at one point, I was dreaming that maybe you could get something concerning the Hodge conjecture with this. Okay. So for the Hodge conjecture, you start with X, and you take a class inside, PP type, and then, of course, you want to say that it's represented by something holomorphic. Okay. Of course, let's say over Q or whatever, it doesn't matter. That's not the main point. So you take the type PP. Okay. Then one idea is to minimize the volume. To do it. Okay. You minimize the volume. The trouble is that nobody knows how to use the conditional PB type. Okay. And also, when you minimize the volume, regularity is a big problem. Okay. And when you look at the situation like a geodesic, you can minimize the length or you can minimize the energy. So minimize the energy actually gives you regularity more easily. The price you have to pay is that you need a model for it. If you just minimize the volume inside, then you didn't need any model because you just take anything representing a class, minimize the volume. But here, if you want to use the energy, then you need this model to define it. Okay. So the model, of course, if it has Kaehler structure, then it's fine. Of course, you say that, well, you need some curvature condition, but the curvature condition is just helping you to try to get existence when you try to minimize. Okay, so even if you assume curvature condition is still the trouble. So in a way, you are getting some Hodge conjecture type problem, but not using the condition of the type of the cohomology class. Instead, you are using the other direction. You are using some cycles. Okay. So what are the conditional cycles? In this case, the conditional cycle is it is topologically representable by something compact Kaehler. Yeah. And then you say, well, what happens to the various types? Okay. So at one time, I try to get this sort of a dual version, which is easier. Then you ask what the PQ type for this. Okay. The PQ type for this actually is the case of Cauchy-Riemann manifold structure. At that time, I tried to do it. I couldn't do it, and before I came here, prepared to talk, I still couldn't do it. Okay. But so I tell you what this thing is. Okay. So the analog of this type, for example, if you have a class, and is represented by a CR manifold. So this is usually called a CR manifold. Okay. With M complex directions, and let's say R real directions. Okay. This means that let's call this X. Okay. So the tangent space of X admits a part that is invariant under J. The part that's invariant under J has complex dimension M, and then the rest is R-dimensional. Okay, and so this is CR manifold, and then if you look at the PQ type,
so each point is like that.
yeah, each point. Let's say smooth everything, just like Kaehler. Okay, and you also assume that it has some Kaehler structure as well. Yeah. Okay, and you have PQ. Let's say you have PQ class. No, and on the manifold now. Okay, so this one is the definition of Cauchy-Riemann. Okay, so you take an ambient manifold M, for example, and then you have a class, you have a cycle. Let's say it can be represented by this, for example. And then if you look at a PQ class here, of course, when you evaluate here, if P minus Q is bigger than R, then it would be 0. Just there's not enough space for it. So in this case, you're sort of having some filtration. Yeah. Okay. Then the question is, can you reproduce it? At first, I thought it would be trivial, with simple things to modify, but in fact, it's not. Okay. So when you take a CR manifold, you want to get some holomorphic functions on it. Well, holomorphic in the sense that it's a CR function. Then some strict positivity will be required. Yeah. So even if you assume the right kind of positivity, I still cannot do it. And then you say, what is the difficulty? Okay. Suppose you even assume forms.
What are you trying to do?
Okay, you try to say that if you have a cycle that has such a representation, then there is a CR map into it. just like the case of holomorphic map, okay, or conjugate CR, whatever. Yeah. So that means that you look at the cycles, okay, with a certain, well, this idea of type, then it could be represented. Yeah. Of course, it's a long way from this. It's actually very different. But even this is not that simple. The reason is that, suppose look at the case of a sphere, let's say of a unit sphere, 2n minus 1 inside Cn, okay, given by r equal to 1, r is the distance to the origin. Okay. Then you take dr, and you take j of that. Okay, so actually it's usually denoted by CR. Okay. So this one here is a kernel. Okay. Okay, this is on this thing here. Okay. The kernel here gives you the complex direction, of course. Yeah. And so what happens is that you can, of course, take the Kaehler form here, pull it back. Okay. Then on the holomorphic part, then it's like a Kaehler form. Okay. But when you want to do this kind of thing, then you have to wedge this guy here. Besides the Kaehler form to a certain power. Say from a certain power. You're going to wedge this part. So certain power, let's say the Q or something. But then let's say something about the holomorphic situation. The holomorphic situation, the proof actually goes as follows. Over there, you take d bar of f, let's say alpha, you wedge d bar of beta, h alpha beta bar, wedge the Kaehler form a number of times, let's say q times, to get the top degree. After you take the d bar, and then you integrate this. Okay, that is the technique of integration by parts. Okay. The main point is that this is a negative situation, and the Ricci doesn't enter from the domain. The dual one, the Ricci enters. So if you try something like this, what happens is that you have to put this thing in. This thing is not closed. So if you assume also that it's closed, then of course it's triviality. On the other hand, this is the kind that is not interesting. The interesting kind actually is the one that is strongly pseudo-convex and so forth. Okay. So then one tries to handle this and try to say that you are able to produce a CR map. The question is still open. I'll get back to this when I have time. Okay. So this is still one of the open questions. Another dream there. Yeah.
Can you say that open question just a little more precisely? So you have sort of a Hodge conjecture for PQ classes, right?
Yeah, but this is a cycle version.
Yeah, sure. But what approximately is the open question?
The open question is that suppose your manifold has the correct negative curvature. Actually, is a negative complexified sectional curvature. Yeah? And then there's a class that can be represented by smooth something like this. Yeah. And you may need some strong pseudo-convexity and so forth. If you have the flat case, then it's just the usual thing already works. If transversal, the invariant measure in the normal direction and so forth, then just the whole point works the same way. Yeah. But if you have the strong pseudo-convexity, then the question is whether in that class, homotopy class, you can represent it by CR map. CR map means it's holomorphic along these holomorphic directions, the same way. Yeah. Yes.
Is that flat easier? Can you do something for M and abelian variety?
No. Flat means that means the following. Means that if you take the complex foliation, okay, then you have the transversal invariant measure. So you could just stick in the form in the normal direction. I think in the literature there are papers by those Kemper and Tongde, I think, about Riemannian foliation and so forth. So they look for harmonic situation that would be analogous. But then it would be a straightforward generalization of that. Okay. So another way that I was dreaming about in those days when I was here. That was trying to get rid of the model. So the trouble, of course, is the model, the class, okay, the class model. And so suppose you are able to represent it by something holomorphic. Let's say V, holomorphic already. Okay. Inside your ambient manifold M. Okay. Of course, you really don't know what the model is until you get to it. However, you can always, let's say the dimension, complex dimension is P. You can always get a branch cover over it. It's finite one map. Okay. Branch cover over PQ if it's holomorphic to it. Okay. Then you say, let's use this as a model then. Because if you can solve it, then you can always get this thing a model. Okay. But then the trouble is that it would be a multi-value map from here to here. Let's say this lambda sheets. Then you have get P here to the symmetric power of this guy. Then the trouble is with the singularities. Okay. In a way that's more related to Kurt's talk now. There's this singularity. Okay. So later, I saw the paper of Gromov and Rick Schoen about harmonic map to the singular metric space given by Broussard-Tissot buildings. Okay. So the Broussard-Tissot building, so one simple example would be like this, that they were trying to explain. Okay. So it's more related to this cone manifold idea that Kurt was talking about earlier. Then, so they call this Y. Okay, this is just three things. Okay, and then you have the two-dimensional thing here, and you want to understand what harmonic means here. Okay, so the way they did it is that they construct a Y prime to explain it, so that by opening this up, it becomes a half plane. Okay, and then use the map into this, and then the half plane here would go from here, projecting down. Okay. So there they use the notion of harmonic map into a singular metric space. And so I tried a bit on this. It's not the same. So the question remains whether you are able to do this. If you have a class that could represent it as a topological branch cover over it, many value to map, and a map into it. Okay. So this moves you closer to the original Hodge conjecture situation, because you are not trying to minimize the volume. And of course, the question still, how do you use PP type? How the PP type fits into this picture? That's not clear either. Yeah. Now, I want to move on to another development in Kaehler geometry that stemmed from Dan's work and also Magula's work. Is the notion of superrigidity. So superrigidity deals with something slightly different. The idea is that you have M into N. Again, N has non-positive complexified sectional curvature. Okay. But you assume that M is locally symmetric, let's say, and the rank. So, for example, the quotient of irreducible.
Positive or negative?
This one here, semi-negative, semi-positive, semi. Oh. This is right. Okay. Okay. Non-compact type. Yeah. So here is the same kind of thing. Locally symmetric and non-compact type, rank at least 2, let's say the universal cover, irreducible, and so forth. And then, again, you want to consider the map, harmonic, and here you want to say that it's totally geodesic isometric embedding. Okay. So the the idea there is that, again, you can take the harmonic representative in the homotopy class, and here you want to get, instead of what we had earlier, when we had this thing here, you would get the perfect square plus the curvature term. The perfect square, actually, it looks like nebula d bar of f, okay, together with the curvature term, which I explained here. So if you know what this thing is, you could always expand out and get the formula. So the main point is what perfect squares you want to use. And in the case of Kodaira's vanishing theorem, when you have a, let's say, 0p form, omega, okay, then the positive vanishing, what is being used is this thing square, and negative is this thing square. So this one here, the same type as here. This one is different type. Okay, so when you take strong rigidity or super rigidity, the whole problem is how to interpret the square, the perfect square. So in the Mostow kind of strong rigidity, this is being used. Of course, omega is the d bar of f. Okay. So in Magoulet's super rigidity, what is being used is this thing, square. So this thing has two indices. Let's say alpha and maybe jk of f alpha. Yeah. And of course, it's clear what to be done for this one. Here is h alpha beta bar, for example. Okay. Even if it's a real manifold, you can always complexify. Okay. So the question is what to do with these. There are actually to be four indices. JK, let's say the LM or something. Yeah. So what is being done here in this situation is simply use the JK bar or GM L bar. Actually, is being raised to contract it. Okay, so that's being used there. And you could use other four tensors to do it. Actually, it's this idea of Calabi for this kind of rigidity that you use curvature type tensors. What do you mean by curvature type tensors? You could use, for example, the curvature from here, and then you can use the standard curvature. What is the standard curvature? For example, the standard curvature for constant sectional curvature is xk, maybe xj, dxk here, j, dxk summation, okay, jk. Yeah. That's just constant sectional curvature. Or you can use constant holomorphic sectional curvature, which would be like dz alpha, dz beta bar, and then tensor, the same thing, summation. Okay. Okay. And so what happens is that you could use certain linear combination of the curvature here together with the tensor from the constant sectional or constant holomorphic or even constant quaternionic curvature. And you put this into here and do the integration by parts. That's how you get all the super rigidity known from this statement. Okay. So this was published in a paper I wrote up with my student Mark and also his student Young quite a while ago. Okay. So this is the super rigidity. Another thing what I want to talk about is the case of positive curvature. Sigge sort of hinted at this. So what happens to the positive curvature? Okay. So if you take positive curvature, you have two troubles. First trouble is existence of harmonic maps. Because you don't have a way of controlling it. It doesn't have Ascoli-Azella. Okay. So how do you handle it? Well, it was first handled by Sachs-Uhlenbeck. So if you have already some L2, third derivative L2, you're minimizing. So you have this Sobolev thing, you know is good. Okay. But you want something more. The trouble, you don't have something more. Okay. And so it may happen that you have the bubbling situation. That means you have you want to get the higher order Sobolev and it's concentrated somewhere. Okay. So you have the bubbling. So Sachs and Uhlenbeck show that if you want to get the minimizing the energy, any manifold, then you may end up with this thing represented by not one, but a finite sum because of the bubbling. Okay. Now, this bubbling process actually is analogous to Maury's construction of rational curve for final manifold. So actually, in Maury's case, he forced it to decompose by fixing 2 points and deform when you go around once, and he forced it to give you another one. And so this is the bubbling process. And actually, I wrote a paper with Yao at one point to solve the Frankel conjecture as alternative way of doing it, alternative to Maury's, to show that when you have positive tangent bundle in the Griffith sense, then it must be projective space. And there, you use the bubbling process, but you use second variation of the energy to make sure that you could represent the fundamental class of the H2 by a holomorphic map. So this is the first difficulty. And one problem, which is still outstanding, is to show that when you have a final manifold, M, that means that the canonical line bundle is negative, is compact, complex. Okay. And in that case, there should be rational curves inside. So rational curve means holomorphic map from P1 into it. And Maury proved it by using characteristic P. And the challenge still remains how to do it analytically. You try to do it analytically, you have this trouble of bubbling. But the bubbling actually is how Maury used to do it. Okay. So then you say, how are you going to handle this? Okay. You handle this actually to use the bubbling, and then you pull back the tangent bundle, and it would be something harmonic. That means you pull it back. And you take df. Okay. df is this valued 1,0 form. Okay. And this is actually holomorphic. You pull it back because it's harmonic. Okay. So then you get a holomorphic vector bundle on this thing after you tensor with the canonical bundle here. And then you can decompose. Okay. The trouble is that decomposition, one is with positive curvature, one is with negative curvature, and so forth. And then the idea, I couldn't quite do it, but the idea probably is workable, that you have some directions that are positive and you move. Okay. You have another direction that is negative, then you move its complex conjugate structure. And you move it so that somehow they come together like this. And then you sort of cut off like this to minimize further, to make sure that indeed you get a holomorphic curve from P1. But I couldn't quite do this. So this is the first difficulty. Okay. So what happens to the second difficulty? The second difficulty is the curvature term. Because the curvature term is the wrong sign. I mean, how do you handle it? Yeah. The curvature term is a wrong sign simply means that you have some eigenspace. For example, you have some eigenspace for 0 eigenvalue. Okay, that's the trouble. Okay? So you may have some eigenspace that's not good. If you are able to kill those, okay, then you are okay. The question is how to kill the bad eigenspaces. In complex geometry, there are two known ways of doing it. One way is to use symmetry. That was started by Mostow when he was trying to solve the Nuremberg problem by using some version of Schrödinger inequality. So the Nuremberg problem is the following. Is that you take S2, you assign a curvature function, K, and it has to satisfy Gauss-Bonnet, of course. Okay. And then after it satisfies Gauss-Bonnet, then you want to say that you are able to find a metric, assuming that. Okay. So you want to solve it, what happens is that you get the standard metric, let's say D, maybe call it G. GS2. Okay. And then you conformally change it maybe to a certain conformal change, okay, with a conformal factor. Okay, maybe E 2U or minus 2U, I can't remember precisely. Okay. Then what happens, you get an equation like this, 1 plus Laplacian U for this thing, E K E minus 2U or something. Yeah. Okay. The Gauss-Bonnet comes from this guy. Yeah, this guy. And you have trouble solving it when you do integration by parts and so forth. It's precisely because you have this bad eigenspace. Okay. So Mostow's way of killing it is to assume antipodal symmetry. So assume, because this kind of thing is like Sobolev inequality, actually Schrödinger inequality. You have a constant. So if you have antipodal symmetry, you cut the sphere into half, okay? And then the constant is correct. So you try to handle this by symmetry. Another way to handle it, the second way, is to make things vanish at certain points, vanishing somewhere. This idea is like Siegel's idea of using Schwarz lemma. If you have a cohomology class represented by something harmonic, or even represented by cocycles, if you assume vanishing at certain points, sufficiently high order, then you force the thing to vanish. Yeah. So then one tries to do this. Okay. And this actually, there's a big theory to it. It's called multiplied ideal shift theory. Multiplied ideal shift is that you want to solve the Debye equation because of the obstruction. You cannot do it, but you assume that your original thing vanished already somewhere, some good place. Okay, that belongs to what is called multiplied ideal shift. Then automatically you can do it. Okay, this actually is also related to the bumping technique of Grauert. Okay, let's go back to the CR case. The thing that we had before. Okay. The CR case actually should be related to the vanishing theorem, because when you do the strong rigidity, okay, what is being used is Kodaira's vanishing theorem for negative line bundle. Yeah? So suppose you have the curvature and you have CR manifold. You don't have the vanishing theorem for CR manifold, because even if you have something strongly pseudo-convex, and you have a class here, suppose the strongly pseudo-convex CR manifold is part of something holomorphic. But the class here may not be extendable to the whole class. There's some obstruction in the center. Okay? So in general, you have trouble. Okay? And one wants to say that you are able to solve the d-bar equation and get some holomorphic section or holomorphic function. Well, it has this idea of bumping. So you take some complex hypersurface and then bump this and say that the cohomology there is the same, and then that enables you to produce something holomorphic. Regardless of what happens here. Okay. And the thing involves this vanishing here. That's related. Okay, so there are two ways of doing it. Let me explore a little bit this symmetry situation. Okay, symmetry situation. Then, of course, if you are given a manifold, then the question is how much symmetry do you need? I mean, in the case of S2, you have antipodal symmetry. In general, how much symmetry do you need? Let's be generous and make it even the globally symmetric space. Well, that, of course, is very nice. Okay. So then it becomes the question of strong rigidity for such spaces. The question is strong rigidity for compact symmetric, Hermitian symmetric manifold. What happens? Now, in general, this is hard. Even the case of P3, for example, okay, and it's related to the non-existence of complex structure on S6. You blow a point, okay, then these two things are related. Okay, and in general, you don't know how to handle this. Okay. So, and also there's this first difficulty. So a very weak version of this is the situation of global non-deformability. When you look at strong rigidity, of course, there's a version of just local rigidity or rigidity. And if you have compact Hermitian symmetric manifold, you know that is rigid. Okay. And strong rigidity is so much harder because of all the difficulties involved, and mainly the first one. So the weaker one is global non-deformability. So if you assume that you have a holomorphic family over the disk, so that pi inverse t is xt. For example, this is biholomorphic to, let's say, Pn for t not equal to 0. Suppose holomorphic family. Then the question is what happens to this guy here? Okay. That actually bypasses this thing, because you know what happens, how to relate the neighboring one to the limit one. Okay. So this I actually solved in the case of Pn. And my student Junmo Huang solved it for hyperquadratic. But for the other spaces, it is still not possible. Okay. And so this is the compact version of it. And then you say, how was this proved in the case of Pn? Okay. In the case of Pn, actually, it is proved by using vector fields. So you take Euler vector fields. So point, so Euler vector field will be something like this in affine coordinates. Okay. So you take the Euler vector fields on xt, and you could actually extend them all the way to x0. Why can you extend them? You can extend them meromorphically, no trouble with that. And then you multiply by an appropriate power of t, it becomes holomorphic. The trouble with this kind of extension is that the semi-simplicity is no longer there, because you want to, the vector field will be given by the semi-simple group, actually a simple group here. And when you get the limit of vector fields by multiplying by power of t, then when you take the Lie bracket, then when you multiply by t, because this is quadratic, okay, this thing actually becomes 0. You multiply by different powers of t. Okay. So it becomes some a billion subgroup inside. Yeah. And to make sure that it doesn't happen, you have to do some counting by the Chern classes and so forth to do it. So in general, it is not still not possible how to handle it. And then you say, what happens to the case of higher rank? In the case of hyperquadratic, you can still do it. The reason why Pn is easy is that when you count, the vector fields always vanish, this kind, on a hypersurface, namely the infinity hyperplane. But in general, higher rank, this doesn't happen. And in the case of higher rank, actually, there are some other things that come into the picture. Let me say something about super rigidity in this regard. So a moment ago, we were explaining super rigidity by looking at M and then going to N. And then N here has complex curvature, let's say the EF or something, or E bar, F bar. Let's say go to 0, something like this. Okay. And then you want to show that you have geodesic, totally geodesic isometric embedding. This actually is related to the Schwarz-Pick R4 situation. The Schwarz-Pick R4 is the situation of this to this. Okay. And then the curvature dictates how the distance is being contracted. Yeah. And then it gives you Picard and so forth. In particular, it tells you that if this is more negative, you cannot get the map into it if you have a complete situation. Yeah? Okay. So the compact situation, you can get a map into it. Yeah. So here, when you deal with this situation, it's not holomorphic, but if you use this kind of thing, it is analogous to this situation. That this is non-negative, and therefore, the map there must be, the flat ones must go into the flat ones. That actually is the reason why you get super rigidity. And also, there are enough flat ones around, so they crisscross. Okay. So here, in this picture, you want to do the same thing. If you have some higher rank ones, and you get the limit, you have something crisscrossing. But then in the limit, they sort of a bubbling situation. This situation of degeneracy is the same as the bubbling. You get to the limit. And that still cannot be controlled. If you can control the bubbling, so for example, by assuming that the limit one also is a Kaehler metric to start out with, then a bubbling can be controlled by the volume. In that case, you could do it. Actually, this was done by Mock and Wang under this condition. So the strong rigidity or even global non-deformability for the positive case is so much harder somehow, because you have to control the curvature. I think I'll stop here. Thanks.
Can you connect these measure rigidity theorems of Marina Ratner with some of these ideas, or use the measure rigidity to add to these ideas?
I don't know. I mean, let me. Maybe I can use some of the question time to say some more of what I try to say. Okay. So this is a very good question, because there are actually two problems that are related to this. Okay. One problem is the this S6, okay, has no complex structure. That's hard. Nobody could do it. Okay. So there is a non-compact version of it. Non-compact version of it is the Bohr V6. And you take a discrete subgroup isometry group, and you take the compact quotient. Okay. And you could get one that has almost complex structure, sort of a dual situation with this. Okay. And then you want to say that that one cannot be integrated. Okay. Now, how do you show that one can be integrated? That is more related to Dan's idea of going to the boundary. So you get the tangent bundle decomposed into two pieces, okay, because the 1, 0 and the 0, 1. Yeah? Okay. And so the main point is that the discrete subgroup here has more symmetry than can be allowed for a complex manifold. That's the key point. Okay. So when you get to the boundary here, go to the limit of these things, get to the boundary, you can get some algorithmicity so far as volume is concerned. Okay. But that is not enough to give a contradiction. Okay. To give condition simply means that there's no almost complex structure to start out with. Okay. And you need some smoothness more than measure. So your algorithmicity is strongly more measure. And that is precisely the differential equation for integrability comes in. So you want to say that when you have integrability, then you get an extra smoothness. And then you get to the limit, you get a contradiction. So I try a lot on this, but I couldn't. It's just my knowledge is not enough to handle this algorithmic situation. But this is more related to Dan's work of getting to the boundary. And there's another question also. Well, maybe I shouldn't take away your time. But I have no idea how to use Wagner's. Yeah.